Okay, cool. I'm starting a little bit late. All right, so let's see. One thing, Dr. Sardashti brought my attention to a question which I think I didn't answer. You helped me see I didn't answer it very well. And it is a kind of a subtle question. Remember, we had the Gaussian wave function, and we took the complex conjugate, multiplied it by itself to get the probability. And he was pointing out maybe that I should have been a little bit more explicit about how to do that. So in other words, if you have something like exponential of a complex number squared, and you want to take the complex conjugate of that, is it obvious that it would be something like this, that we just take the complex conjugate of everything inside? Yeah, okay, and yeah, okay, so that I didn't pay enough attention to the question. I think the question was more subtle than I had understood. And Dr. Sardashti obligingly told me after, when we had lunch afterwards, I think you missed something that was going on in that question. Okay, so when is this going to work? In other words, are there any functions where this isn't going to work? You just simply flip I to minus I everywhere. You see it. Okay. And there are functions where that can be a problem, but you'll never encounter them in this class. That the functions, and there's a whole subject of this, which is complex analysis, or just analysis in math. The behavior of complex functions. When do you have to be careful? Where are the pitfalls? So the general answer is that for solutions to the Schrodinger equation, this is never a problem. And so you'll not encounter this as a problem, meaning as a pitfall, anywhere in this book. Everything we do and follow the rules pretty simply. Everywhere there's an I or a complex number, you just take the complex conjugate of that number. So to help you to see how that is, I mean, it's a deep subject. It would take more time for me to help you to see how this works. And that subject, if you want to understand it better, pick up a book on complex analysis or complex functions, and then we'll talk about that. But I'll help you to see how it is that we're generally safe in this class. You don't need to worry about it. You just do, as I said, flip I to minus I anywhere it occurs. So let's check this one. That's true. Let's take something simple. Start with just this. Okay, so there are a couple different ways to check this. Use Cartesian coordinates, or you could use polar coordinates. Either way, it should work both ways, right? Because they're equivalent. So we could do x plus iy squared, and then we take a complex conjugate of that. And is this equal to x minus iy squared? Okay. And so you can work this out. Oops. X squared minus y squared plus 2ixy. Complex conjugates. That same thing as x squared minus y squared minus 2ixy. Okay, and it is. See how that works. And then if you do this in polar coordinates, it's actually even easier. Because we have in polar coordinates let's see, we need r squared e to the I 2 theta, so that's c squared. Complex conjugate of that, is that equal to r e to the minus I theta squared? See that it works. Okay, so we're just taking small steps here because you got to work your way through this. Any integer power, this will work. Even negative powers. Minus 2, e to the minus 2, same thing will work fine. Okay, you can see how to demonstrate that from these examples. Square roots are a bit of a problem. Any roots, so fractional powers can be problematic. You have to be careful. We'll never encounter a wave function like that. The reason for that is because the solutions to the Schrodinger equation there's some guarantee about what's called analyticity, analytic functions. So in general, we just don't encounter in this course functions for which this is a problem. Okay, so you would, in order to figure it out in general for a problem, a function, for example, the exponential, is it true? Is that true? So we go back to the definition of the function. So e to the z, remember, use this definition. Okay. And from this, you can see it's quite clear that if I take the complex conjugate of this, so it's taking the complex conjugate of this. So now we go back to the any integer power. We just go ahead and do the complex conjugate inside, right? We just demonstrated that. So I can show you them, I explain them. This is the same as that, which is then, by definition, z star. You're safe. Okay. So there are functions for which this doesn't work, but they're not. We'll not encounter them in this class. Yes, you do one. It's a little difficult. I couldn't come up with one this morning that was really simple, but I'll tell you do that one, and you can, because there are two roots. Square root. So this is not this is a multi-value function. And that can cause problems because when you take a conjugate, you might end up with the wrong one. So that's an example of one. It doesn't. I think logarithm work problematic. There are ways to, even the ones that don't work, you can kind of patch them together, and over some domain, you can make it work, but not for all values of the argument. Whereas these functions, these rules work for all values of the argument. So in the technical terminology, any function that's called entire, it works for entire functions. And functions that are not entire, meaning that they're, okay, this is related to another word called analytic. Analyticity is related to differentiability. So these functions are infinitely differentiable. But in any case, these are terms that I don't really have time to explain. There's restrictions on this, and this is what should all be explained in any good book on complex analysis. So you're safe in this class. Just be aware that you can get into trouble with functions just taking complex conjugates. You do have to be careful, but you won't have to do that in this class. And the reason is that of the nature of solutions to the Schrodinger equation, you're not going to encounter this kind of functions. So you're okay. But that's a good question. It's an excellent question, and I'm sorry I didn't pick up on that in class. So I apologize, and I hope I amended that some. It's a very good question. Okay. All right, there was another question. We were talking about the barrier, the delta barrier. And we had the wave function expanded. We had the wave function in the two different regions. So psi to the left, psi to the right. We matched these, and we said at x equals to 0, we had to have this true because the wave function has to be continuous. And then the question came up in class, another good question, which was, this looks like a kind of a conservation probability, but it seems kind of funny because, or I think the question was stated as conservation of mass. There's no mass. This is not mass, of course, but it is related to probability. So why don't we have the relation that B plus C is equal to A? We don't have that. And the answer is that these are probability amplitudes, not probabilities. So we could write it this way. Right, let's solve for A. And now let's take the, excuse me, sorry. Let's take the complex conjugate, multiply it by itself. So we take A star A over here. We take C minus B squared. So we're multiplying C minus B times its complex conjugate. So we get 4 terms. Right? C minus B star multiply C minus B. It's C squared plus B squared. Then we get these terms 2. Did I do this right? Yeah. Right. Okay. 2 B star B star C plus B C star. Okay. All right. Now, and then we solved the problem, and we said that C is related to the C squared is related to the transmission probability. B squared is related to the reflection probability. So if C over A is the transmission and B over A is the reflection, what happens to this? And it looks like there's a violation of probability conservation. But if you go and look at the solution, this combination, B star C, B and C are of course not 0, but this combination does vanish. So B is the solution to B for your homework. You should have gotten this. It's also in the text. B over A, also called little r, and C over A, which is little p. These where gamma is that ratio of the energy to the potential barrier height. Okay, I guess it's the square root of the energy. Okay, so now if we take, and you could multiply these by A, for example, D is RA here, for example, and C is equal to TA. Keep it in this form. Okay, so let's take the magnitude, we can take the magnitude of B squared, the magnitude of C squared, add them together, we'll get 1, and we'll get A squared. What about this term? Well, we look at this, you can see that B star times C is going to be imaginary. Right? Let's multiply this out. B star C equal to I over gamma, I gamma over gamma squared plus 1 times S of magnitude. Whereas BC star is going to be the complex conjugate of that. So we work out BC star negative I gamma over gamma squared plus 1. So the sum of these two terms is 0. This term vanishes. And so we do recover the conservation of probability. And that's because B and C have this particular relationship between C and B. When we take B star C, we get a purely imaginary number. So we add it to itself, it cancels out. Add it to its complex conjugate. Cancels out. Okay, does that help? See how the probability works out? You have to remember that these coefficients in the wave function are not probabilities. They're called probability amplitudes. And they're kind of strange things because we don't have anything corresponding to probability amplitudes in ordinary mechanics. The closest thing we have to it is when we have the relationship between the electric field and the intensity of the light. So the intensity of light in EMF, intensity of light is related to the sum of squares of the electric and magnetic fields. So I should say it's proportional to, depends on the units exactly how you get this relationship, but it's proportional to E squared and B squared. This is the closest analogy we have to this sort of thing, where the but this is real here. The electric field is real. I don't mean it's not a complex number. We can use complex numbers even in describing electromagnetic field. But it's physically, it's a physical thing. It's a property of the quantum. This is the physical thing. It's a property of the quantum. Whereas when we're talking about wave functions, that's not so straightforward. It's not something that you can call a property of the quantum. Not so straightforward. Right? Remember the understanding of the wave function, which is on the inside front cover, gives us information about the behavior of the particle and the guiding wave, but only in statistical way. Don't have details about how the guiding wave, the wave function doesn't give us all the detailed information about what the guiding wave is doing. So that's where the analogy breaks down. We know we do have detailed descriptions of electric and magnetic fields. So the wave function isn't like that. It's sort of like it, but not like it. Probability, amplitude, and there isn't any other thing like it anywhere else in physics. So this is a bit strange. So its connection to the probability is through the Born rule. So I hope that helps. So study the solution to the homework for today, the transmission and reflection of the delta barrier. So let me ask you a question then, since we've seen this reflection coefficient. So as a function of gamma, which gamma squared, which is just like the energy of the particle coming in. So there's some kinetic energy. And we saw we could calculate the see, so this is the transmission coefficient, this is the reflection coefficient as a function of the energy of the incident energy. And they add to 1. Those two things add to 1. So let's take a step back now. Because if there were an infinite force in Newtonian mechanics, if that's the only thing that's operating on the particle, it'll never make it through. But we have in this case that for low enough energy relative to the strength of the barrier, we only get some fraction through. And some fraction is reflected. So what's going on? How do we understand that? Yeah, Mr. Russ.
Looks like if like the more energy the particle has, the more they actually get to the barrier.
Yes, that's right.
But does that mean,
Well, why should any get through the barrier?
you said it's like part of the dynamic structure was causing it?
Well, it is the guiding wave structure. It's the delta barrier is not the only thing that's acting on the particle. Particles are also encountering the guiding wave structure. Two parts to the guiding wave structure. One is the resonant part. The other is the stochastic part. And so there is another actor, there is another agent that's acting that can help to get the particles through the barrier. And that's only seen implicitly in the Schrodinger equation. It's not made explicit. So it doesn't appear as whereas the potential is an explicit term in the Schrodinger. So the way to see more about that, by the way, this as an extra credit. This is the wave function on the left side of the barrier. And we now have B in terms of A, right? That was the reflection coefficient. So we could pull this out. Okay, so this is all multiplied by that. Let's look at the probability. Is now a function of X. And so the probability is not uniform on this side. There will be interference terms. You get an interference between the incoming wave and the reflected wave. And so you can see some of the influence of the guiding wave structure here because you get an oscillatory probability over here, which is a result of the interference between the incoming and the outgoing. So that helps to illustrate some of what the guiding wave is doing. The other part is that the guiding wave can help it penetrate through the infinite potential. Infinite in the sense of it's also infinitesimal. It's infinitely high, but infinitely thin, infinitesimal. Okay. So the influence of the guiding wave structure is there, but it's implicit in the Schrodinger equation. And it expresses itself as a probability. So we can calculate the probability of making it through or reflecting. And remember what that means. I'm going to set up 1 million copies and I'm going to pass them out. And each one of you is going to make a determination. In your case, did the electron come back or did it make it through? It doesn't do both. Each one of you sees only one of those. Did it coming back or are you making it through? And then we add them all up. We say, what fraction of everybody saw it get through? And what fraction saw it reflect? And those should match the transmission and reflection probabilities that we calculate. It's an ensemble. So,
can you why is it for the probability of that? Why is it useful to have it in terms of x when there's like like you're saying, like there's an infinitely small point where it actually is occurring, the reflection? Because like if it's before the wall, isn't there, like, how are you measuring? Sorry for not having the right formulation, but like, if it's before the wall, that means it has not been reflected or transmitted yet. And if it's after the wall, doesn't that mean that it has to have been transmitted?
yeah.
So like, how does the probability change?
How does the probability change? So on the left-hand side, you'll get this oscillatory probability. On the right-hand side, it's uniform.
So like, but like, why is it coming in? Why is it not that? Like, why is it oscillatory coming in? Is I guess the question.
Because it's an interference between these two different pieces. You're setting up a standing wave of having a right and left traveling part set to the standing. If you're a little worried about if you have this probability, how do you P of X, how do you sort out what part of it is traveling to the left, what part is traveling to the right?
Yeah.
Okay, we're going to come to that in about 2 pages. Right. Because what we're going to do is calculate the current, probability current, which is a lot like an electric current. It's just particle is charged. It will be a probability current. You'll see, even though the probability is stationary, it's not changing. There's actually a current. Some of it is traveling to the right, some of it is traveling to the left. You'll be able to sort out 2 pieces individually. And so we'll come to, I think we'll answer your question when we do the current. All right. And we'll come back to examine this again when we have current.
Thank you.
Yes. Yeah.
I want to ask, sorry, it appears as if this is deep on.
Seconds. I need to. Okay. Sorry. Go ahead.
If energy, you keep getting like ensemble, majority of the particles are have actually really high energy. Does that mean majority of them are actually going to get through? Are actually going to go? They're going to what do you call it? They transfer? What do you call it? They tunnel through.
What's your question?
If the energy is really, really high, does that mean majority of them are actually transferring through?
Yeah, right. That's what the transmission and reflection coefficients, right? Here's the reflection, here's the transmission. Where they cross, now the majority are making it through.
It sounds silly, but it's just like it's interesting. I thought like a very small fraction.
No, depends. If the energy is sufficiently high, you can figure out where the reflection and transmission equal each other, and that will give you the threshold energy, which most of them get through. And then for any energy higher than that, it gets higher and higher. It's not a small amount. Depends on the barrier though, and the energy. Okay. All right, well, here's another problem though that we could look at. This is an example, the honors section and extra credit. The problem of what if we have a delta hole, not a barrier, but it's a dip in the potential. So the potential now, so in other words, we can go back and look at what happens if we consider that E naught bar is negative. So what happens in that case? Well, if this were the only thing that we're acting on the particle, you would expect 100% transmission. So it just rides over the bump. The bump does influence it, but it doesn't repel it, unlike the barrier. Okay. So we can look at two different problems here. We can do this as a bound state problem. Because there may be a bound state here. The question is whether it's kind of weird because it's the attraction, the region of attraction is infinitesimally thin, but it's an infinite attraction over a very thin region. It's kind of strange. You might think maybe there isn't going to be a bound state, but there is. And then the other one is a scattering problem. So when we had the delta barrier, we just did the scattering problem. There's no sense in looking for a bound state for a repulsive potential. Not going to find it. Okay, so let's look at the scattering problem. Yeah. So the scattering problem is expressed in the same way. We have an incoming wave at some energy. And once again, now we get a reflection and a transmission. And in fact, all of the formulas come over to this, carry over, and he shows that in the book. He continues it on the page. But it's kind of strange here. Why is there a reflection? If the agent, the only agent for this potential, then you wouldn't expect anything to be reflected. So the guiding wave structure is influenced by the potential and does something enough here that there's some kind of mismatch that goes on that some of the particles get reflected by the guiding. And in fact, it's very much the same plot. You just flip C bar to its negative. And so this plot now is as a function of the energy. It's the same one again. It's the same, it's kind of strange, but it's the same plot as a function of gamma squared. Okay, so this was the transmission reflection. I'm sorry, transmission. So if the energy is low compared to this depth of this well, you'll get a lot of reflection and strain. Again, if the energy is sufficiently high, it will make it across, and you'll get most of the particles. So that's another example of the guiding wave is having this influence on the particles. And strange, and again, all the calculations are giving us our probabilities for the ensemble. Each one of the copies of the ensemble, each member of the ensemble is going to get a reflected particle or a transmitted particle, not both. No fractional particles. Okay, so the other one is a bound state. This also supports a bound state. And go through this in the homework, the solution. The function looks like this. Again, we're going to divide it up into two regions. But the energy now for the bound state is negative. It's below zero. So we have zero here corresponding to no kinetic energy. Right? That was the zero of energy. We could have a little bit of kinetic energy and possibly make it through. No kinetic energy, well, there's nothing moving. We actually have solutions to the Schrodinger equation, one solution to this Schrodinger equation, where the energy is negative. So it's a bound state, and the wave function looks like this. So let's see how this works. Okay, so the wave function in region 1 now there's only one term. We don't have a plane wave coming in to scatter off the potential. We have only one possibility. It can only be this. So let's try something of this form in the Schrodinger equation. So remember the Schrodinger equation now, where x is not equal to 0, Schrodinger equation, independent Schrodinger equation. It's like this. But E is negative here. E is less than 0. Oops, should be double prime. Okay, so let's try a solution of this form. Let's do e to the kx. Like that. Not ikx, but kx, it's real. So we substitute that in here. We get e energy is equal to minus h bar squared k squared. So that works if the energy is negative. The energy is positive, you have to have a complex exponential. With the negative energy, you have a real exponential. Okay, so then we have this relationship, E is less than 0, and is equal to minus h bar squared k squared over 2n. Well, k is equal to the square root of negative 2n. There are two roots, plus or minus. So we could start off with, let's look at this side. We could start off here, do it this way. I actually have two possibilities on the right side. We have plus k, the positive root, and we have the negative root here. So what is the negative root? The first function. It decays exponentially this way. How about that one? Blows up exponentially. That would mean the problem is we have anything, if d is not 0, we have some probability becoming infinite, growing in without bound. And that can't be. You can't have a probability that it becomes infinite. See why? Because you remember the probability is a fraction. So we couldn't, there'd be nothing. That is, that it would be more than 1. Couldn't normalize terminology. So we have to set this term to 0 in order that we have finite probability. Otherwise, the probability is infinite. Remember, we have to have that the total probability is 1. If we have a term like e to the kx, then the probability is going to be divergent. It will not converge. Probability over there is going to be infinite. Okay, so this is the only term that we can have in this region. In this region, it's the opposite problem. This term will blow up if x is negative infinity. So we have to throw that one away. So what does this look like? It's decay to the left, right? X is negative here. So this is decaying to the left. So now the wave function looks like this, and we have to apply the conditions that we had before. We still have the wave function is continuous, but the slope in the slope in the wave function is discontinuous. You can see it very explicitly here. The slope isn't the same on the two sides, right? There's a cusp. The difference in the slope on the two sides is related to the strength of the delta potential, which is negative. Okay, so we have psi 1 is 0 is equal to psi 2 is 0. That means A is equal to C. same coefficient on both sides. And then when we calculate the slope, is equal to minus 2m d naught bar over h bar squared. I'm sorry, it's positive. Yeah, positive. Times psi of 0, which is equal to a or c, right? Those are the same. Okay, so it turns out then that this puts a restriction on the value of k, which is related to the energy. So there's just one value of the energy. So there's only one bound state. But there is one bound state. Yes, sir.
You said last part of the time.
Okay, so I want you to look at the solution for this. I sent it out. This part, you know that A equals to C, but this gives you a condition now that comes out to this K. So let's look at the slope on the right side. It's going to be minus K, C. It's negative. On this side, it's going to be K, A, e to the K x, and at 0, it's just going to be K A. So it's minus K A, but A and C are equal to each other. Right from above here. A or C, doesn't matter. So A drops out. We have them as a condition on K. So K is equal to M naught. There must be a negative sign someplace that I've messed up. No, I'm sorry, that's correct. Yeah, there must be a negative sign somewhere that I messed up because we should come up like this. Not for the negative sign. So I've messed up the calculation somewhere here doing this quick, but it's in the solution. It's also in the book. Okay, so this is what we should get. And K is related to the energy. So the energy is fixed. There's one value for the energy for bound state in this problem. So unlike the particle in the box where we had a bunch of bound states, we've got only one. There's no excited states, it's just the ground state. Yeah.
I noticed in the book it did this too, what you just did right there with you not having a bar on it. So is that
Is there a bar?
Do you think it's a typo in the book probably, or
It should be a bar everywhere it is, and then it's part.
okay, all right, so there's not like a physical thing.
It's in the definition of the potential. There's a V naught bar. So that should be what goes through it. Okay. That's what I wanted to go through. So we're collecting solutions to the Schrodinger equation for different potentials. The free particle in a box. Now you can add to that the delta variable. Okay, so let's write down the little table here. Free particle. There are no bound states. Well, the scattering is really trivial. Right? Just right through, left traveling or right traveling. So, yeah, but it's kind of trivial. Okay, what else? We had the particle in the box. Infinite number of bound states. No scattering. There's no scattering because there's no place you can shoot particles from, because the infinite potential outside the box, the potential is infinite outside the box everywhere. So there's no place for you to go to shoot particles from. particles can't be anywhere outside the box. So there's no scattering solution for the particle box. Okay. So the positive delta barrier and the negative delta barrier. I guess you couldn't call it a barrier, the delta well. You'd better take the call. Okay. There's no bound state for the delta barrier. There's one bound state for the delta well. That's contrasted with the infinite number of bound states for the particle in the box. How about them scattering? We did the delta barrier and the delta well. Scattering off both. Okay, so you should, it would be helpful for you to review these, maybe in this way. Look at the two examples for the bound state. We're going to add more on this category. And we're going to add more over here. It might be helpful for you to look at these scattering problems, these three different scatterings. This is trivial. These two are closely related to each other. We're going to add more to both columns. Bound state problems and scattering problems. That's what we're going to be doing next. In fact, I think the next problem, if I remember correctly, look, I've got a book. Yeah, okay. Before we get there, we're going to calculate the current. A couple of gents had to leave. Close to the class. Go. So this is what's next. Coming up next. We'll look at how is the probability flowing, even in the case where the probability itself doesn't seem to be changing. There is actually a current flowing of electrons moving through the system. So like the delta barrier, we shot particles, we got some coming back, some going through. How do we analyze we've got a static probability distribution, but how do we analyze current? There's actually a current. It should be a current of electrons flowing through this system. So we'll go back to analyze that in terms of this current, the probability current density, which will give us how the probability is flowing through the problem. In other words, it relates it to the average velocity of particles in the ensemble. So it's a lot like the current density, the electrical current density, very much analogous to that. Out of the electricity demand. All right, so I've given you no homework over the break, so have a good restful break. Might be a good time to spend a few minutes to review what you've done now. We've got a lot more to do after the break. There's a lot coming. So be a good time to review, make sure you got everything down right. Have a good break, be safe. After the break.